So now that we have a clear definition of what number the letter e represents, we can talk about what the derivative of an exponential function looks like. Now, I'm going to walk through the derivation here, but it's relatively short compared to what we went through to define e itself. If you're just looking for specific examples, then just go ahead, just jump ahead to the next slide, right? And we'll start doing some examples from there. Okay, so to do this, first, I need a function, right? So let's let f of x equal e to the x, and I'm trying to find f prime. Well, to do this, I'm just going to use the definition. F prime of x is the limit h approaches 0 of e to the x plus h minus e to the x all over h. And let's see, I'm going to factor in e to the x out of the numerator there. This is the limit h approaches 0, e to the x, e to the h minus 1 all over h. And because that e to the x, it doesn't depend on h, I can bring it out in front. So this will become e to the x, limit h approaches 0, e to the h minus 1 over h. All right, now here comes kind of the creative step. All right, I'm going to let e to the h minus 1 equal y. All right, now, let's see. I'm going to substitute that into the numerator, but in the denominator, let's solve this for h. Right, move the 1 over, e to the h equals y plus 1. Take the log of both sides. H equals the natural log of y plus 1. So let's see what that does to my limit. This is e to the x times the limit. Hold off on that 2 part for just a second. Y over the log of y plus 1. Now, I want that limit now to be in terms of y instead of h. But let's go back up here to my definition. The limit as h approaches 0 of y is the limit h approaches 0 e to the h minus 1, which is 0. So in other words, as h goes to 0, y goes to 0. So that's what I'm going to do for the limit down here. I'm going to replace this with y approaches 0. All right, now let's see. I'm going to take that y in the denominator and actually move it down to numerator. Did I say denominator? I'm going to take that y in the numerator, move it down to the denominator. So this becomes e to the x, limit, y approaches 0, 1 over the log of y plus 1 times 1 over y. All right, now I'm going to use my logarithm property. I'm going to take that 1 over y, bring it inside as an exponent. So this is e to the x, limit, y approaches 0, 1 over the log of y plus 1 to the 1 over y. All right, now, let's see. I'm going to use my limit properties, right? This is the same, and I'm a little out of room, so I'm going to have to jump up here, right? This is the same as e to the x times 1 over the log of the limit as y approaches 0 of y plus 1 to the 1 over y power. Okay, but here's the cool step. Here's the reason we needed to go to all that trouble to define e in terms of a limit. This limit here is just our definition of e, right? So this whole thing equals e to the x, times 1 over the log of e. But the natural log of e is just 1. So this whole thing here is just 1. This is e to the x times 1 over 1, which is e to the x. And it doesn't get any simpler than that. Remember, way back here at the beginning, right, this is f prime. So f prime of x equals e to the x. About the simplest formula you are ever going to encounter in mathematics. The derivative of an exponential function is an exponential function. All right, so here I just summarize our result. The derivative of e to the x is e to the x, right? It doesn't change. Really special property. This is going a little beyond what we're going to do here, but I'll just put it out there for you. The exponential function is the only function that is its own derivative. Right? This is a really unique property. Okay, so now I promised you examples. Let's look at some examples of this thing. How do we do the derivative of f of x equals x e to the x? Well, the first thing that jumps out to me is I have two things being multiplied together here, x and e to the x. And since I know how to differentiate x, and I now know how to differentiate e to the x, I can use the product rule. Right, so f prime of x is the derivative of x times e to the x plus x times the derivative of e to the x. The derivative of x is 1. So this first term is just e to the x. And the derivative of e to the x is e to the x. So this is plus x e to the x. And that's it. Right, that's all there is to it. This derivative is, like I said, one of the easiest formulas you're ever going to have to work with. All right, so let's look at another one. You can pause it if you like. You want to take a minute, see if you can't do this one yourself. Then turn it back on, and we'll go through it together. All right, the first thing you have to see here, and this is a little tricky for people sometimes, the first thing you have to see is that this is a function composition situation. So what I'm going to use here is the chain rule. All right, and to see this, I'm actually going to go ahead and write this out and make this explicit. I'm going to let g of x equal e to the x, and h of x equal x squared. Then f of x, sorry, let me write this a little further. Let's put the derivatives in here. G prime of x is e to the x, and h prime of x is 2x. Right, now let's do the composition. F of x is g of h of x. So according to the chain rule, f prime of x is g prime of h of x times h prime of x. Okay, h of x is x squared. So this is g prime of x squared. H prime of x is 2x. Or I'm going to bring that 2x around to the front. Put that 2x out here. G prime of x squared. Well, g prime is e to the x. So g prime of x squared is e to the x squared. And that's it. All right, there's my derivative. Okay, so that's really all there is to differentiating this natural exponential function. So at this point, you might expect us to try to generalize this and look at the derivative of f of x equals a to the x. And well, what happens if we put another number down there? But that would end up being the long way around. Instead, we're going to talk about the derivative of the logarithm function. Because once we've got that derivative, it's going to be a lot easier to figure out what this one is.